Hi guys, and very welcome to this tutorial, to the second part of Mastering Houdini Destruction Simplified. And this part will talk about simulating debris. If you don't watch the first part, I will highly recommend to do this because we'll use a couple techniques that we already discovered in the first one. The topics today are, we will dive inside and look at the SourceDebris SOP node in Houdini. Then we will simulate debris out of the inside faces. We'll just take already cached ground destruction that we already have, and using speed and distance threshold, we will just control the emission of our debris points. Then we will build our custom debris geometry, and we will just copy debris geometry into debris points with randomizing a size, type, and orientation. And then we will go to the SOP solver and learn how to emit our RBD debris. And then we'll integrate our ground cache geometry inside our DOP network as a collision. Okay, let's jump inside Houdini and start. This will be a result that we would like to achieve. In this part, you see out of our already simulated ground destruction, we will emit and simulate our debris. This setup will be fully procedural, and you'll be able to control amount and behavior size of your debris. Okay guys, first I'd like to walk through with the setup and then we'll build it from scratch. You see, this is a scene that we left from our first part. We're just taking the points and transferring the movement of the points to the high-res geometry using transform pieces. I will use for simulating debris not the high-res geometry. I will use the proxy geometry for considering the time. But if you have a close-up, I will highly recommend to use the high-res geometry. First thing you have to do, you have to unpack your geometry to get inside faces to be able to emit from inside faces. As you see here, we don't have any groups here on a packed geometry. And when you unpack it, you get this inside and outside faces. Then what I do here, I calculate the velocity to be able to get a speed, because if you look at your debris source, what it's giving us this simulation. And I already set here the speed threshold to 5. I will show you how I did it, how I check the speed, and how I set it up. And we also use here the distance. I activate the distance here, distance attribute. And here I'm just saying, hey, you have here min distance, max distance, everything within this threshold. Keep. If is not in this threshold, just delete, because I put in a group debris here, and then I blast it here. You see, now we're left only with the pieces that have distance within this threshold. Okay, then I just delete unnecessary attribute. And as you already know, we would like to copy our procedurally generated debris geometry to the points here, and to be able to control the size, orientation, and also type, we have to create here a p-scale attribute and randomize it. Then for amount, I just create also one custom, the custom setup that you can just, I just show you what it does. If you have some debris here, maybe you go here, and you can reduce or increase the number of, that's a bit of the debris you see now. You can control also the amount of debris. To be able to see what this node does, we have to first look at the debris creation. What I did here, I just take a sphere, I modify it with a mountain saw, and I do a Voronoi fracture, and I get this whole debris pieces here. I just do exploded view that we can look at the pieces here. And what this loop does, by default, if you try to copy to point these geometries, every piece here by default will have its pivot point in the middle of the grid. And if you copy to point it this way, you will get the offset. What you have to do first, you have to bring your piece to the middle of the grid and make this piece has a pivot point on the origin. And you see we're using here match size. We pack it because, as you already know from the first part, we need packed geometry with a unique name on the points. And you see I promote the name attribute from primitive to point. And now we just go inside attribute from pieces. What this node does is create the randomization for our debris geometry on these points. Imagine you have about 2,000 points here, or maybe 20,000 points here, and I like to get the geometry that I have here. Maybe this will be, in my case, these are 400, and I like to randomize them within this amount of incoming points. And this node does it for us. Now you see every point here has a name. You see we created here the names here. If you look at your geometry spreadsheet, it goes from debris 0 until 4 to 3. And you see now here on these points, we have the same thing. This points have now the randomized names going from 0. Because we don't have enough points here, you see we have only, that's why it's not going to. But if you have more, then you will get the full range. If you have maybe 2,000, it will be the range of what you see on this geometry. Okay, and then we use copy to point node, and we take in consideration piece attribute. And what's happened here, if you look at your setup, your points now are, or your packed geometry is copied to these points. If you look carefully, you see we have randomized version, because we have different, or we have randomized p-scale attribute, and also it take in consideration the type, and we have fully randomized pieces for simulation. To be able to understand what this node does, or this wrangle node does, first we have to understand the idea behind the simulating RBDs. Because the first part, we just took some initial geometry and we just move this initial geometry with a collider. In this case, we will emit every frame this debris inside our DOP network. That means every time every frame, you will get these names inside your DOP network. And as you already know, our rules from the first part that you have to have name attribute on the points and they have to be unique. But if you will emit the same geometry inside your DOP network, you will get the duplicates of name and you will get errors here and your setup will not work properly. That's why we just take in consideration the frame number, and we're just saying, okay, just write me the new name. The name will be debris, put the PT num here, and also the frame number. And every frame, you will get the different name, unique name for your simulation. Let's jump inside the DOP network and see what's happened there. As you already know, we will use here the SOP solver to be able to emit our RBDs inside the scene. You're already familiar from a first part with these nodes here. with the RBD packed object, and the rest, here's the collision, here's the ground plane RBD solver. What's new here is this SOP solver. If you dive inside the SOP solver, what we're doing here, we're just grabbing the geometry from our source debris. You see here outside our DOP network, we have this source debris with a unique name on each frame here. And we're just adding with a merge node this to our RBD setup. And if you activate these fields, they will just adjust the velocity of your setup. What is very important here, you have to also activate the inherit velocity from point velocities, because if you look at our setup here, our packed geometry has also velocity. This velocity is inherited from our RBD ground simulation. Okay, let's see how we can build it from scratch. Actually, I forgot to mention one important thing here. As you already know, we use these transform pieces and get our debris out of our proxy geometry. And this geometry I use inside debris simulation as a collision. You see, if you jump inside here, you will see that my static object pointing to this collision object. Okay, let's just build it from scratch now. First, let's move our proxy geometry with these cached points. I will use this transform pieces node, and I will just connect not the high res. I choose here my proxy geometry, and you see now this point cache will move your proxy geometry. Now we need our inside and outside groups. By default, on a packed geometry, we don't have any groups. And we have to unpack it. And you see now you have your inside and outside groups. And let's create our source debris or debris source and connect it to the first input. And let's see what we have by default. If you activate your debris source, we have to also go back to and activate the simulation, otherwise we will get nothing here. And you see what you get here, you get these whole points appearing on the first frame. What it's doing now, it is creating debris source from everywhere. First, let's see how we can use the inside faces only. Just click on this guy, and you see now the simulation will be only from the inside faces. But it's also now, we don't need this behavior because I like to have some criteria. And the first criteria will be the speed. I will say, okay, if the speed is 0, there is no velocities, I don't need any points. And then if the speed increases, I like to have within a threshold simulated debris points. Let's see how we can set it up. If you look here, you can just activate the speed threshold. By default, it's set to 0 here. And if you play now, let's set it a little bit up, maybe to 5. You see now it just disappearing. Why? Because we don't have any speed, because our PCs don't have any velocity. If you look here on your unpacked geometry here, we don't have any velocity. Let's first calculate the velocity. I will use the trail SOP for that. And I choose here a calculate velocity. I just temporarily disable my simulation here. And let's look at the velocity here. You see, if you play your simulation, you get the velocities here. Okay, now we have velocity, but this guy, look for speed. As you already know from a first part, to calculate the speed, we have to use length vex function. I would say here speed. And we use here f at speed is equal would say length function, and out of our velocity. You see now we can look to the geometry spreadsheet. We have the speed. On the first frame we have nothing here because there is no movement. But if you play a little bit forward, you will see you will get the maximum and minimum. I think the maximum. You can look. I will stay maybe within 0 and 16, and that's why I use here 5 here. What's happened now? Everything above 5 will emit the debris. Let's see how it works. Just go back here. Don't forget to activate it, otherwise you will get nothing. And you see now, only the pieces, they have velocity more than 5. Let's just disable this visualization off. Okay, getting simulated. But this is one criteria that can use here. The second criteria, what I like to use, is the distance between our faces here. For example, you see here, if this guy now just move with a constant speed, it will always just emit debris. But actually what's happened in nature, first time when you have some, when the geometry splits, you get this debris and that's it. That's why we have to set another attribute. It will be a distance between, and we will set the min and max distance, and within this threshold we'd like to have this emission. Let's see how we can do this. Third thing to do is activate the distance attribute. And now you can look at the distance attribute in your geometry spreadsheet. You see now you have the distance. You have to resimulate it. Oh, no, it's working also from out of the box. You see we have a distance now, and between 0 and 0.5, and it will increase if you go somewhere here. It will be 0 to 0.4, because the pieces now we have 0.7, because some pieces fly away from each other more than the others. And I like to just delete everything, but and keep only pieces they have maximum and minimum distance. Let's create the setup. I will use Wrangle. And first I like to create my min and max distance. I just say here float, and I say here min. It will be channel F. I would say min dist. Don't forget the semicolon. I just copy this guy and I do another. I create another variable. It will be max, and we will say here max dist. And I would say here if my current distance, it will be f at dist, is greater than min, and also f at dist is less than max, put these guys in a group. The group will be e@group. group. With this group prefix, you specify a group. Now I give a name to the group. It will be debris. Everything after the underscore become a group name. And I will say here it's equal to 1. Otherwise, I like these points have the group equal to 0. Okay, now let's just use a blast node to get rid of this not necessary points. I use a blast. We're working with points. That's why I choose the points here, and I say here debris. And you see now you can say delete non-selected. Let's see what's happening here. Okay. First we have to specify min and max because everything is 0 now. And I would say from 0.2 till 0.5. I like to have it. And you see now you have some reduction. Let's see here, delete non-selected. And you see only the faces emitting now the points within this threshold. You can do a little bit more or less. Okay, great. Let's continue. Let's create our debris geometry to be able to just scatter or just copy these geometries on our already simulated or emitted points. Let's do this. I create a sphere. I set the sphere to polygons, frequency to 10. I use mountain SOP to make a little bit. Let's see what we have here. Now let's use ISO offset to get, actually we can use here the points from volume. Now we have this kind of points here. I would say I like to have point separation 0.2 maybe, because I like to have less of them. And we do a little bit jitter. And let's see how many points we have here. About 70. It's a little bit too little. Let's do 1. Maybe 1, 2. I like to have maybe 500 or something. Okay, this is enough. And I will have now Voronoi fracture and exploded view to see how our setup looks like. We have this pieces now. Okay, let's continue with bringing these points to the origin, because as you already know, the pivot point of each geometry piece have to be in the middle. Otherwise you will get, if you copy the point, you will get the offset. Let's see how we can do this. Our Voronoi fracture already created this name attribute. That's why now I can use for each name primitive. If you look here and activate your single pass, you'll get each primitive. But if you look at the grid, this pivot point of this piece is here. Let's bring this guy to the origin. We use here a match size. You see now we have the pivot point in the middle. What we have to do now, we have to promote this, or first let's pack it, because we need packed geometry. And I like to transfer, because if you look carefully here, this is one of the very nasty nodes, these value attributes. I would say, okay, name I need. And now what you can do, let's promote attributes, because as you already know, we need a pack attribute, or we need a pack primitives with the name attribute owner points. And I say from primitive to points, originally will be a name. And if you look here, you have first your name on your primitives. And now you have the name on the points. You have a packed geometry represented with 1 point, and you have name attribute on the points. But the name is not correct, because piece 3 is like a name the Voronoi fracture gave us from out of the box. Let's change it. If you go to your Voronoi fracture and under piece prefix, we'll say debris. or debris. Okay. And I like to put underscore also here. And now you will see, now we'll have debris underscore 3. If you disable your single pass, now we have unique names on the points, and you also have packed geometry. Now we'll use attribute from pieces node. What this guy does is just take the names of the geometry and spread them randomly, or apply the names randomly to these points. And then if you use the copy to point, it will just take in consideration the name attribute, and it will just take a name of the point, look here on this geometry container, and just grab the correspondent packed geometry with the same name. Okay, you see here, if you hover over it, you need your geometry library. We put it here, and the points here. And if you look here, in a geometry spreadsheet, you have your debris from 0 to 334. And here you will have the same thing, 0 to 334. But as you look here, we have some problem, because on this side, we have a name attribute without the underscore, and it's creating here the name attribute with the underscore. Why? Because the name already exists here. If you look here, we have the name attribute here. We have to first delete unnecessary attributes. For example, we can delete everything and just take maybe edge, life, velocity is very important, and nothing else. Let's create attribute rename, or rename attribute. And we'll say, okay, I like to delete everything, but velocity, but age, maybe we will use this, and also life. And I think it's fine. Now you see we have a point with no name. Very interesting. We just delete everything. Sorry, you have to just do it this. It's saying, okay, delete attribute. I like to delete everything here. And, sorry, everything. And I like to keep the age and also life. Perfect. Now, if you look at your geometry spreadsheet, we don't have any okay, we have edge, life, and also the attribute. You can also delete the group with a group delete, but maybe we will use this group here underneath. Okay, great. Let's see now, if you look here, now our name is here without underscore. It's going from 0 to 334. Let's use the copy to point node and see the result. If you do it this way, what's happened, now it will take everything here and copy to every point here. You see, now we have some kind of setup like this. But if you activate this name attribute, now what it's doing now, it's taking here the point, look at the name, and grab the correspondent packed geometry with the same name out of this library. But as you see here, our packed geometry is too big. Let's create our p-scale attribute to be able to control the size of these pieces. Okay, we will use for that the wrangle, and we'll say our f at p-scale, p-scale is equal. I will use here the channel ramp. This ramp name will be size, and I will use here the random function of my e at ptnum, it will gives me the value from 0 to 1, and I can just adjust this value within this ramp. What I also like to do, I like to multiply it with a channel. I rename it to size mult. It will be the multiplier for everything, just like main multiplier. Just click on this guy here, and you see now we have size multiplier. We can increase this, and now you can just adjust the ramp. For example, I like to have many little pieces maybe and a couple big ones. Okay, great. Now we randomize the size, and now let's see how we can randomize the orientation. Okay, for randomizing orientation, I will use the attribute randomize node, or randomize attribute. By default, this node randomizes the color. I will say here orient. Orient is also the global variable that Houdini recognizes for rotation. Then we'll set this dimension to 4 because this is matrix. And what I like to do here, I would say here inside the sphere. Now you see we have a randomization of the rotation. Let's see how we can just adjust the amount of this debris. Because there is 2 ways you can do it. You can adjust it here, for example, your debris source. But I don't like this because normally what I do, I cache also the debris because the inside of this debris solver, inside this debris SOP is also a solver, and it's calculate the result every frame. It's take a little time. That's why I always cache it here, and I control it after I cache it, the amount of the debris here. I show you how we can do this. We will use a wrangle node or blast, but in this case I'll use wrangle, and we will say if the random from e at ptnum is less than some threshold, then just remove this point. We use remove point vex expression, and we remove it from input number 0. And which point we like to remove? We like to remove the point with a point number ptnum. Okay, great. So if you click here, now you can just specify how many points you like to have for your emission. According to our part 1, what we need for RBD simulation, we need the RBD packed object and also unique name on the points. We achieved this already in our setup, but as you already know, we like to emit it every frame. And if every frame I will emit these names here, I will get on the second frame duplicated names. Now let's see how to make them unique within changing the frames. I will use here the wrangle, and let's create the name attribute, unique name attribute. I will say as at name as equal. I will use a sprintf function. You already know what is this. And I do here, I just give a name. I say debris. Debris. And I put here a placeholder. %d is for integer, underscore, and %d again for another integer. And I say here, just take first the point number, and as a second argument, use please the frame. Okay, now let's see. Now your name attribute becomes also the frame number. And this name will be the unique for every frame. Even you have the same names coming out of here. Okay, let's continue to set up our RBD simulation. Okay, let's create first a null to be able to grab these RBD points. I'll create a null here. And I would say, this is my source. And I say debris. Okay. I like to have it black and also showing output. Also, I like to have another null for my collider geometry. As you already know, we already create this here because this is our low-res geometry. And I like to have a collider out of this guy here. You can also do a cache here for speed up your simulation inside your DOP network, but I just do it without the cache. In my setup here, I just copy this guy and I do here. And I will say here is collision and this will be ground. Perfect. Now let's create our DOP network. I would say this will be my debris sim. Dive inside and create RBD packed object. Where's the packed object? Rigid body solver. Gravity force. Gravity force, ground plane, and couple merges. I create first one merge for all collisions and one merge for bring these collisions inside the simulation. As you already know, this collision have to go to the first input. And here at RBD packed object here. Now let's rename it to debris. And let's see how we can grab this debris inside our geometry or inside our DOP network. In a part one, we will just set our source here. But as you already know, we like to have RBD emission. For this, we use SOP solver. I connect the SOP solver to the pre-solve. And I go inside the SOP solver. This will be our RBD geometry. And I like to use the object merge to be able to merge this object every frame inside the simulation. I use here merge. And I merge this incoming geometry. And the incoming geometry is our here source debris 1. Let's see what we have now. Just go back and I will simulate it and come back to you with the result. Okay, let's see the result. I just hide the ground plane here. Now you see what you have here. Okay, great. Now let's see how we can just set up the collision, because as you already know, the collision is very crucial here. And this collision, because we simulated the RBDs and now they are inside this object. Let's go to Boolean data and look at the collision. I just disable the geometry because this is not the collider geometry. And you have to activate it and wait a little bit because, and you see it's looking good here. What you can do, you can just go here and just set the collision padding a little bit down. Something like this. Now you have to resimulate it, or you have to just go back here, show your geometry, and show your collision again to recalculate it. And you see now you have a better representation of your collision. Okay, let's see how we can bring our collision geometry, because you like to our debris to be able to collide with already simulated ground geometry. And also, if you have some drastic effect here like this, you can just let it this way, or you can put our duo that we already learned from the first part, the spin drag and air drag, to get more believable behavior of debris. Let's see how to do this. Okay, first thing first, let's create first our collider geometry. As you already know, let's disable this guy because it will slow down your simulation. I will use here static object, pointing to our created null object. It will be here, this ground. Now we have to go back to see the geometry. And the same thing is imported for this geometry. Just look at the collision. It will be our bullet data. I just disabled geometry and show the guide. And you see we have something like this. It's wrong. You have to first activate this create convex hole per set of connected primitives. And what I will do here, I will also make this collision padding a little bit smaller. And you see now we have proper collision 2. Just disable this. And I will simulate and I will come back to you after it's done. Okay, now I got this, and you see now your debris are colliding with the ground geometry. I forgot to mention one important thing. You have to activate this use deforming geometry, otherwise your collision will not move. Okay, great. Let's just apply the forces and we're done. Okay, as you see here, the debris are not flying so far. Now they have some kind of air drag here. And let's see how to just bring our debris out of our DOP network. If you jump outside your DOP network, you will see that everything coming out of this DOP network. But we only need this debris object. What you have to do here, instead of everything, you just grab your debris object. And now you see you have only your debris. This is a conclusion time. Now you have very flexible debris system that you can use for every destruction scene. I would say that's it for this tutorial. The next steps are the third part, where we will build together also very flexible dust setup for your RBD destruction. If you like this one, subscribe my channel, and I will see you in the next one. Bye.